The AF Harvey Prize is a really prestigious prize operated by the IET.
My nominator is the Dean of Engineering and he's from the UK here, and so for him the Harvey Engineering Prize has always been the holy grail. It's what he recognises as being the most highly sought after and the most prestigious of engineering prizes internationally.
I'm very thankful with the funding that comes with the AF Harvey Prize because it gave us additional resources to continue our work and to explore new, exciting research directions.
Over the past 2 decades, my team developed technology to stimulate the spinal cord, which allows us to restore walking after paralysis. And today, thanks to the prize, we have the opportunity to use the same technology to aim at restoring upper limb movement in people with tetraplegia. I would like to thank you wholeheartedly to provide us with the opportunity to achieve this next breakthrough.
With the support of IET Harvey Research Prize, we will take this research further and particularly try to understand how we could apply smart materials to have dynamic control of those antenna performance.
I obviously do feel extremely proud to have won the award, both for myself but particularly for my research team. I think it's fantastic to have our work recognised and gives us the opportunity to take it forward.
Hi, I'm Julian Young, President of the Institution of Engineering and Technology. Welcome to this year's Harvey Prize lecture, Realising the Untapped Potentials of the Terahertz Spectrum, delivered by our incredible winner of the 2021 AF Harvey Engineering Research Prize, Professor Mona Johari. You just saw a short film showcasing some of our remarkable past winners of the prize, who have all been achieving great things since winning the funding. The prize, which is an impressive sum of £350,000, was set up in 2010 with a trust fund from the late Dr. Arthur Frank Harvey. It's awarded annually to phenomenal researchers working in radar and microwave, lasers and optoelectronics, or medical engineering. Our search and selection panel looked globally for potential candidates, drawing on their expansive international networks to reward the most innovative workers in these fields. Professor Mona Johari, a professor of electrical engineering and the director of Terahertz Electronics Laboratory at the University of California in Los Angeles, is the 11th winner of the prize. Today we'll hear from her as she delivers her inspiring lecture, and afterwards you'll have the chance to ask her some questions. She has made significant contributions to the development of ultra-fast electronic and optoelectronic devices and integrated systems for microwave, millimeter wave and terahertz systems by using novel materials, nanostructures and quantum structures, as well as innovative plasmonic and optical concepts. So congratulations, Professor Johari, on this thoroughly deserved achievement. I'll be back with Professor Johari after the lecture, so get thinking of any questions and pop them in the chat. We'll try and answer as many as we can.
Today I would like to tell you about my journey to explore and realize some of the untapped potentials of the terahertz spectrum. As you know, the use of electromagnetic waves has revolutionized how we communicate, exchange information, and monitor health. It is hard to imagine how our lives would have been without cell phones, computers, internet, and X-ray machines. But at the same time, it is so exciting to learn that there are still many unique potentials in the electromagnetic spectrum that remain underutilized, which could have otherwise transformed our lives in ways that we cannot even imagine. The terahertz regime is one of these underutilized parts of the spectrum that offers very unique functionalities. For example, many chemicals have unique spectral signatures at terahertz frequencies that allows us to identify and characterize them in a non-invasive way. Also, many optically opaque materials are more transparent to terahertz waves, allowing us to reach visually inaccessible environments for a variety of imaging and sensing purposes. Also, the energy of terahertz photons are way lower than X-ray, UV, and even visible photons, allowing us to interrogate biological tissue without any danger of ionizing or destruction. Also, since terahertz waves are highly absorbed by water molecules, they give very high image contrast that allow us to identify between malignant and benign tissue and identify infection, inflammation, burn tissue, and blood vessels. Also, as we move from radio frequencies to terahertz frequencies as carrier signals, obviously much higher data rate communication systems would be enabled. I'm sure you all agree with me that these are very great potentials and great applications. However, the unfortunate truth is that existing terahertz systems are limited in their efficiency and functionality. And the reason for that can be traced back in the electromagnetic spectrum where terahertz frequencies are situated. They are between the regimes that are traditionally covered by electronic and optical systems. As you know, conventional electronic systems have an upper bound in the highest frequency that they can cover, mainly because of restrictions of transistors. Also, conventional optical systems have a lower bound in the lowest frequency they can cover, mainly because of restrictions in the bandgap energy of the semiconductors they use. So while both optical and electronic communities continue to push the device performances they build to cover more of the terahertz band, we take a hybrid approach in my group where we utilize the complementary functionalities of photonics, electronics, and plasmonics to make more functional terahertz systems. For example, we have been using photoconductive antennas which are commonly used for generation and detection of terahertz radiation in different imaging and spectroscopy systems. These photoconductive antennas are generally composed of an ultra-fast photoconductor integrated with a terahertz antenna and illuminated with an optical beam where we have terahertz frequency information embedded in its envelope. This can be done two ways. Either we can use femtosecond optical pulses where their envelope is very short in time, so in frequency it will be very broadband, covering parts of the terahertz spectrum, or we can heterodyne two optical beams with a terahertz frequency difference, and as a result the envelope will carry the beat terahertz signal. When these optical beams are absorbed in the photoconductive material, electrons and holes are generated and their concentration will fluctuate at the terahertz frequencies that we have in our light. Now, if we apply a bias voltage to the antenna, we accelerate and drift the carriers to the antenna, and we feed the antenna with a current that carries the same terahertz frequency information. And as a result, we will achieve either pulse or continuous wave terahertz radiation. Please note that these photoconductive antennas are fully reciprocal, which means they can also be used for terahertz detection. In order to do terahertz detection, we don't apply an external bias voltage to the devices and we let the received terahertz field accelerate and drift the carriers. As a result, the photocurrent that will be induced as a result of this interaction will carry the intensity and frequency information of terahertz waves. These photoconductive antennas are very popular tools that are used extensively in terahertz systems, mainly because of their simplicity, their room temperature operation, and the fact that unlike nonlinear optical processes, they don't have a threshold in radiation. Also, the efficiency of these devices can be higher than nonlinear optical processes because they're not limited by the Manley-Rowe limit. That means, for example, when I want to generate terahertz radiation, per each photon, I can generate one electron-hole pair, and if these electron-hole pairs are transferred to the antenna in an ultra-fast way, they can generate multiple terahertz photons. So technically, the optical to terahertz conversion efficiency of these devices can exceed 100%. That being said, when we started working on photoconductive antennas, the efficiencies were nowhere close to 100%, and they were in the order of 10 to the minus 2, 10 to the minus 3%. So we have looked into the physical mechanisms that reduce this efficiency, and we realized the way carriers transport in the substrate is really the cause of this low efficiency. As we accelerate and move the carriers with a bias electric field, we expect to gain more and more velocity, but carriers start scattering from the semiconductor lattice, and that puts an upper bound on the maximum velocities we can achieve. As a result, that limits the number of carriers that can reach to the antenna in a sub-picosecond time scale to efficiently contribute to terahertz generation and detection. To address this problem, my group has been investigating the use of various metallic nanostructures and plasmonic structures that can be embedded in the active area of photoconductive antennas to make light-matter interaction much more efficient. So if we don't have a way to increase the speed of carriers beyond what physics limits us, we can at least manipulate light and concentrate carriers in areas that they have nanoscale distances from the antennas so that more carriers can reach the antenna in an ultra-fast way to contribute to terahertz generation and detection. We have first demonstrated this concept in 2013, where in an experiment, we developed two photoconductive antennas with the same radiation properties, while one of the antennas carried these plasmonic electrodes at the input. The plasmonic electrodes were configured in the form of a grating and were designed so that in response to the optical excitation, carriers were generated very tightly next to the antennas. As expected, experimentally we observed that compared to the conventional design that did not use the plasmonic electrodes, we achieved 50 times higher radiation powers, and when used as a detector, we achieved 30 times higher detection sensitivities. Now imagine using these plasmonic terahertz sources and detectors in a terahertz imaging and spectroscopy system. We can easily achieve at least 1,500 times higher signal-to-noise ratios, which obviously enables a lot of exciting applications. Well, while this work was really the start of the next explorations that we have done on plasmonic photoconductive antennas, after this point, we have looked into scalability and applicability of the technology to various imaging and sensing modalities. So, like conventional photoconductive antennas, plasmonic photoconductive antennas give us all the design flexibilities that we need, for example, to change optical radiation from pulse to continuous wave by just changing the optical pump source from pulse to heterodyning optical beam. Or in order to operate at different optical wavelengths, we can simply change the photoabsorbing substrate to be able to effectively absorb and accelerate the carriers in the substrate. For example, a very popular optical wavelength that we use for terahertz generation is telecom wavelength, at which very compact and low-cost optical lasers are commercially available. Also, by specific design of the antenna that we use, we can simply achieve the polarization states that we are interested in, the broadband or narrowband operation that we are interested in, as well as high tunability. Also, we have explored how the use of arrays of these photoconductive antennas can allow us not only to combine the radiation from all elements in far field and achieve higher terahertz powers, but also because the phase of the terahertz radiation follows the phase of the optical beam, we can do a lot of interesting phase front manipulations in the terahertz beam for various beam forming purposes. So since we have excellent tools in optics to manipulate phase front of the optical beam, like spatial light modulators, we can manipulate phase front of the terahertz radiation for example, focusing and defocusing the radiation and beam steering. So also I want to mention that while these 2D plasmonic structures that are fabricated on the surface of the semiconductor offer significant enhancement in radiation powers and detection sensitivities, however, still they lose many of the carriers that are generated deeper in the substrate and are far from the contact electrodes. To address this efficiency limitation, we have explored 3D plasmonic structures that are embedded inside the photoabsorbing substrate, and this way they can allow stronger light-matter interaction at the nanoscale. So for example, here you see that by using 3D plasmonic structures, we can capture carriers that are generated as deep as 500 nanometer inside the semiconductor, and compared to 2D plasmonic photoconductive devices that offered us 2 orders of magnitude enhancement in terahertz radiation powers, with these 3D plasmonic contact electrodes, we gain an additional order of magnitude enhancement in radiation power. And we are very excited that now we are able to achieve more than 7.5% optical to terahertz conversion efficiencies. That is bringing us closer and closer to the 100% efficiency and even higher that we theoretically expect from these devices. Here I want to bring to your attention a specific implementation of these plasmonic photoconductive antennas that offer a lot of new functionalities because of their specific structure. Instead of using a lumped antenna element that we know based on conventional antenna designs, we use an array of nanoantennas that are placed in a distributed fashion so that they can excite surface plasmon waves when excited with the optical beam. So this kind of configuration offers 3 advantages to us. First of all, because of the distributed nature of the design, we can pump the device at very high optical powers to achieve very high terahertz radiation powers and detection sensitivities, which would have otherwise been limited by thermal breakdown or carrier screening in the substrate. The second advantage is that because the radiating elements are very small compared to the wavelength, we can achieve very broadband radiation that conventional antennas don't offer. And finally, in order to maintain high radiation efficiencies while using very tiny antennas, we use this distributed configuration and combine the collective contribution of all the antenna radiations that add up constructively in far field to achieve very high radiation efficiencies. So through this design, we have demonstrated record high terahertz radiation powers exceeding 10 milliwatt, and also very broadband radiation exceeding 6-7 terahertz. Another point is that, like other photoconductive antennas, these plasmonic nanoantenna arrays are reciprocal, so the design can be optimized to offer very high terahertz detection sensitivities. As you see here, we have specifically engineered these nanoantenna arrays in a way that not only they offer very strong light-matter interaction at the nanoscale at the tip of antennas, but also this time they offer a very strong spatial overlap with the terahertz field so that we can achieve very high detection sensitivities. Now, by using these plasmonic nanoantenna arrays as terahertz source and detector in a time domain terahertz spectroscopy setup, we have achieved very high signal-to-noise ratios and dynamic ranges. Signal-to-noise ratios exceed 100 dB in a snapshot. So this has enabled a lot of new applications in my group. For example, here I'm showing how we detected ammonia at very low concentrations using our terahertz spectroscopy system. Here I'm detecting ammonia at 1 part per million concentration, which is less than the ammonia we carry in our breath. A 1 centimeter gas cell of ammonia is placed along the terahertz beam path, and as you can see, we were able to resolve all the spectral signatures ranging from 1 terahertz past 5 terahertz. And this is thanks to the very high sensitivity of the spectroscopy system. This result is very significant to us because ammonia, acetone, and isoprene are very important biomarkers for kidney failure, high blood cholesterol, lung cancer, and liver dysfunction. And all of the signatures of these diseases are already present in our breath. However, because of the low sensitivity and specificity of the existing tools, we were not able to use breath analysis as a non-invasive medical diagnostics mechanism. And now, with these high signal-to-noise ratio terahertz spectroscopy systems, the prospects of these applications are very bright. Also, I would like to mention that there are a lot of other interesting physical phenomena that can be explored with these plasmonic nanoantennas. As I mentioned, we have a lot of interest in pumping the terahertz devices with telecom lasers because of their high quality and low cost and compact nature. However, one challenge that we face when we use telecom optical wavelengths is that in order to absorb light efficiently, we have to use short bandgap semiconductors that have low resistivity. That means when we apply a bias voltage to accelerate carriers, we introduce a lot of background current, which can cause thermal breakdown and does not allow us to really push the limits of these devices to high power generation. In fact, we were able to, thanks to these plasmonic nanoantennas, make a totally passive terahertz emitter thanks to the naturally induced built-in electric fields that are already existing at the surface of semiconductors. So please note that when you terminate the surface, a semiconductor lattice at the surface, because of the dangling bonds, you pin the Fermi energy level, and that naturally provides you a strong band bending. And that gives you very strong electric field at the surface of the semiconductor that can be used for wavelength conversion. However, nobody was really able to utilize these fields in an efficient way because they're very shallow. So what we have done is that thanks to these plasmonic structures, we bend light as is incident on the device and couple light efficiently to the surface areas where we have these strong built-in electric fields to achieve very efficient optical to terahertz conversion. Our approach is significantly more efficient compared to other passive optical to terahertz converters based on nonlinear optical phenomena, spintronics, and photodimmer effect. In fact, another advantage that this technique has is that because radiation is initiated through these optical nanoantennas, one can manipulate the spectral, spatial, and polarization state of the radiation while converting from optical to terahertz domains. Another advantage is that unlike other passive optical to terahertz converters, we have very low constraints about intensity of the light, focus, phase matching conditions, magnetic fields. So this is such a flexible and easy to use design that our nano antenna arrays can be simply glued at the tip of fiber to directly generate terahertz radiation out of a fiber. As you can see, with this very simple design, we were able to generate very broadband terahertz radiation with signal-to-noise ratios exceeding 100 dB out of a fiber. And I also should mention that the efficiencies we achieve through these devices are at least 4 orders of magnitude higher than nonlinear optical processes. Another feature of these plasmonic nanoantennas is that Although there are 2D plasmonic structures that enhance light-matter interaction at the surface, and still they might lose some of the carriers that are generated deeper in the substrate, but they can be easily combined with a back reflector embedded in the substrate to form a plasmonic nanocavity to recycle all the photons and provide very high efficiencies. In this work, I'm showing how a distributed Bragg reflector embedded in the substrate, and in fact epitaxially grown with the substrate, allows us to confine light very tightly in a very thin photoabsorbing layer right beneath the plasmonic contact electrodes. And the use of this plasmonic nanocavity can offer very high dynamic ranges and bandwidths in time domain terahertz spectroscopy systems, as we were able to achieve before, but this time these can be achieved at very low optical powers. For example, here you see that at only 0.1 milliwatt optical power, we are able to achieve more than 100 dB dynamic range and a bandwidth exceeding 7 terahertz. This is very significant to us because it allows us for the first time to think of building large arrays of terahertz sources and detectors to implement new modalities for imaging and sensing, which were not possible before because of the high demands that a single pixel terahertz system had. Here I'm showing our first demonstration of a focal plane array that can be used in a time domain terahertz spectroscopy and imaging system, where you see, although the signal strength can vary from corner pixel to center pixel because the intensity of light and terahertz varies across the pixel, but still we can maintain very high signal to noise ratios and bandwidths throughout the entire pixels while achieving an effective number of pixels of 4 kilopixels. So obviously, this will enable much higher throughput systems that were not possible before. In general, the plasmonic nanoantenna arrays have enabled many new applications in my group that we explored together with our collaborators. For example, our plasmonic nanoantenna array terahertz sources and detectors are used by our collaborators in Washington Burn Center, where they use our scanners to see deeper in the burn tissue. As I mentioned, terahertz is highly absorbed by water molecules, so it is an excellent tool for measuring hydration. And that is very important when you deal with a burn tissue, because you want to know the degree of burn wound. You want to know the hydration of the tissue. You want to see how far the burn tissue propagated and how close it has come to the bone. Also, for the same reason, we have been exploring the use of our terahertz scanners for IV access and infiltration monitoring, which is a very important issue, especially for pediatric patients. Also, we have been using our terahertz, high throughput terahertz scanners for quality assurance of a lot of industrial products. For example, here you see that in collaboration with National Renewable Energy Laboratory and Oak Ridge National Laboratory, we have monitored the integrity of various battery and fuel cell electrodes. These are electrodes that carry carbon-based black coatings, and as a result, you cannot really monitor the defects with normal visible cameras. However, as you can see, the terahertz scanner offers very high contrast in the image that identifies various defects, including pinholes and agglomerates. Not only that, it can give us the cross-section image of the layers that allows to measure the coating thicknesses, measure variations in the thickness, non-uniformities, that all are important for the operation of batteries and fuel cells. In another work, we have been collaborating with Professor Moshaverinia at UCLA to use our terahertz scanners to monitor the integrity of dental lab products. Currently, dental lab products are not going through any quality control, and mainly a technician makes them in the lab, and if there are cracks and voids, they won't be able to observe that. For example, here you see what the technician sees under microscope that shows a sample without any defect. When you look at the X-ray image, some density variations, some sharp corners start to show, but it is really when we use the terahertz radiation that gives us layer by layer image of the object that we can reveal, for example, a void in the backside or cracks in the middle. We have also collaborated with US Department of Agriculture to detect different types of aflatoxins in agricultural food products. So terahertz is a very good tool for detecting aflatoxins because first, most of these aflatoxins come from insect damage. So one can detect at terahertz with the right resolution potential insect damage. Also, because aflatoxins have different spectral responses to terahertz radiation, by spectroscopic imaging at terahertz frequencies, you can also identify them. And this is the first time one can detect aflatoxins in a non-invasive way. I have to also mention that this terahertz scanner technology has been now commercialized by a spin-off company that I have co-founded with one of my former students. Now, while traditional imaging systems would like to get a very high resolution information about the object and exactly reconstruct the object, some applications, like image classification applications, don't have as much requirements for the measurements and computation that one needs in typical imaging systems. Here we have collaborated with Professor Ozcan's group at UCLA, where they have trained specific diffractive neural networks that are placed along the path of terahertz radiation, and they are designed so that depending on specific class of the object that was interrogated with terahertz wave, the network will deflect the terahertz radiation into different spatial positions, and with very easy low demand with the terahertz optics with a few number of pixels, we can detect where the classification happens and what type of objects was interrogated. So we have tried this approach on different fashion items, different handwritten digits, and as you can see, in every case, we get a very accurate classification of the object according to the spatial position terahertz beam was deflected to. And pay attention that this is a classification at the speed of light, and as terahertz waves pass through the network, the result and the class is identified immediately. In another work, instead of spatially deflecting terahertz radiation for classification, we have trained the diffractive neural network to embed the class of the object in the terahertz spectrum. So here we have a very broadband terahertz pulse that interacts with the sample, and the information of the sample will be embedded in the frequency band of the transmitted terahertz wave through diffractive networks that are trained for this purpose. So this way, with a single pixel system, you can detect the entire spectrum, and from there you can decode the class of object. In fact, these diffractive neural networks have been very instrumental not only by introducing new functionalities for terahertz imaging and sensing, but also by offering new passive components that we are currently lacking in the terahertz domain. For example, in the visible domain, we have excellent filters and spatial light modulators that can easily allow us to do pulse reshaping and chirping, but such tools don't exist in terahertz waves. Here you can see that again, by specific training of diffractive neural networks, we can take a very broadband terahertz pulse, which is very short in time domain, and chirp it in a very flexible way so that we can change the chirp length, the phase response, and intensity response. In fact, apart from these diffractive neural networks, we have also used various reconfigurable metasurfaces for manipulating spectral and spatial properties of terahertz waves. For example, currently different reconfigurable metamaterials are used for modulating the intensity of terahertz waves, but all of them rely on resonant metamaterials, and as a result, they're not suitable for time domain broadband spectroscopy and imaging system. So here in this work, we have implemented a specific class of metasurfaces which has embedded MEMS switches in it, and it is designed that when we actuate the MEMS switch, we can change the scattering parameters of the metasurface from a full reflector to a full transmitter over a very broad frequency range. Also, in another work, we have implemented resonant metasurfaces with a phase change material embedded in the metasurface, specifically designed to tilt the phase front of terahertz radiation to allow 2D beam steering. While many of the examples I have explained so far use pulse terahertz system for imaging and sensing, I have to mention that there are applications that require very high spectral resolution, and as a result, existing time domain systems might not be suitable for them. One example of that is gas spectroscopy. In fact, more than 98% of the photons that exist in the universe fall in the terahertz frequency range, which carry information about a lot of hot phenomena, ranging from formation of stars and planetary systems to evolution of galaxies. Please note, a lot of these phenomena happen in dusty cloud environments, which are obscuring the visible and infrared radiation, and as a result, terahertz waves are great tools for atmospheric and astrophysics studies. Now, for these applications, the spectral signatures of gases are so narrow that they can be easily missed by time domain spectroscopy systems. As a result, a typical technique to make these instruments is building a heterodyne receiver where the received terahertz radiation gets mixed with a reference local oscillator to down-convert it to lower frequencies in the radio frequency range, where we have excellent electronics to characterize properties of the terahertz beam. Now, for astrophysics applications, we need very high sensitivities, and as a result, the mixers that are generally used are superconducting and hot electron bolometer mixers that require cryogenic cooling. Now, this cryogenic cooling is a practical limitation. For example, here I would like to show you the cryostat of Herschel mission, which was an observatory that costed €1 billion. This observatory carried more than 2,000 liters of liquid helium to just cool the terahertz receivers, and that weighed more than 300 kilograms, where the entire instrument weighed 426 kilograms. Now, you might say, okay, science takes instruments and resources, that is well paid off, but unfortunately, the lifetime of this mission was limited only to 22,000 hours of observation before the liquid helium boiled off. So it would have been definitely much better if we could have done much longer observations through such a big investment. So while this cryogenic cooling remains to be a practical problem in existing systems, the plasmonic photoconductive antennas that we have worked on show great promise to offer similar sensitivities at room temperature. Here we have made a plasmonic photomixer where the photomixer is pumped with a heterodyne optical beam with a terahertz beat frequency. So now, if I use as a heterodyne receiver, this is what happens. When the heterodyning optical beam is absorbed by the semiconductor, electrons and holes are generated, which their concentration fluctuates at the terahertz beat frequency that we can set with our optical source. Now, when we receive terahertz radiation, the induced terahertz electric field in the active area of the device starts drifting the carriers, and the drift current has exactly the mixing product of the optical intensity and terahertz field. So this way we can directly downconvert the frequency of terahertz radiation to the difference frequency of terahertz and optical pump beam, which have a full control over it. So if we carefully adjust the optical beat frequency, we can downconvert terahertz signal to radio frequency ranges where we have excellent electronics to characterize the spectral information. And simply by tuning the optical wavelength of one of these heterodyne optical beams, we can get a very broadband tunability in the terahertz spectrum. So here I show how sensitivity of this heterodyne receiver based on plasmonic photomixers is compared with existing technologies. I'm showing in this graph how superconductor insulator superconductive mixers and hot electron bolometer mixers offer high sensitivities, however, at cryogenic temperatures. And you can see that the demonstrated plasmonic photomixer after 1 terahertz, where superconducting mixers stop operating, offer much better sensitivities while operating at room temperature and while operating very broad spectral tuning range. Now, in summary, I have described to you how the use of the complementary functionalities of electronics, photonics, and plasmonics has allowed us to achieve much higher terahertz radiation powers and detection sensitivities, as well as much higher accuracy and throughput terahertz imaging and spectroscopy systems. I also explained how the use of reconfigurable metamaterials and diffractive neural networks allows us to manipulate the spatial and spectral properties of terahertz wave. Now, while these advances have been transformative and has transformed the course of terahertz field, however, existing terahertz systems are still bulky, expensive, and complex. And as a result, their applications are still limited to laboratory environments and industrial settings. The reason for this complexity is that these systems generally use separate optical pump sources and photoconductive devices, and as a result, they require different optical components and control electronics to interface them. Further revolutionary advances in the terahertz wave for the benefit of the society requires monolithically integrated terahertz optoelectronic platforms that address practical limitations of existing systems. We have all witnessed how bulky and power-hungry early computers were transformed into high-performance microprocessor chips that we are nowadays using in various aspects of our lives, in our homes, cars, cell phones, health monitoring systems, you name it. We are trying to bring a similar technological revolution to the terahertz field and transform existing bulky systems to very high performance, scalable, and low-cost microchips that we can use in our everyday life. Now, towards this goal, the main roadblock that prevents integrating all the components on the same chip is the incompatibility of many of these optical components. On one hand, to make a semiconductor-based laser and amplifier, one requires very high-quality crystalline semiconductor, but on the other hand, one needs a short carrier lifetime semiconductor to introduce the ultra-fast response that photoconductive terahertz devices need. Now, these short carrier lifetimes are usually introduced by ion implantation or incorporating rare earth compounds or growing the semiconductor at low temperatures, all of which will introduce a high density of defects which are not suitable for optical generation and amplification. To address these limitations, we plan to explore a new generation of quantum optical materials and structures that can be used as the backbone of future fully integrated terahertz imaging and spectroscopy systems. I'm very honored to receive the Harvey Engineering Prize and the great recognition, and plan to use the resources offered by this prize to further explore this exciting research. Our research will involve various aspects of the work, ranging from the growth and characterization of these new quantum optical materials, theoretical and experimental studies on underlying fundamental physics of photon generation, amplification, modulation, and detection in these materials, and design and development of new class of terahertz devices and integrated systems, which would be possible through these new materials. I'm very grateful to IET for this great prize and recognizing the contributions of my group in the terahertz field, and specifically the financial support they provide that allows us to do this exciting research. Me and my group are very excited about this research, and we are hopeful that the direction we are taking will transform existing terahertz systems from complex and expensive tabletop setups we have in our laboratory and industrial settings now to scalable, low-cost, and compact microchip that we can use in handheld gadgets for a variety of applications, ranging from health monitoring, medical diagnostics, to environmental sustainability, food and drug, quality control, and security assurance.
Well, Professor Johari, thank you very much indeed for a really excellent and thoroughly absorbing lecture. I know that I handed the prize over. Can we see you? Can we see the prize with you?
Yeah, thank you very much. I really, again, appreciate the great honor and the great prize. And I, again, want to thank the committee for selecting me. Thank you.
Well, thank you. And well, many congratulations indeed. And indeed, it's right and fitting that the first question we have is in fact from Sir John O'Reilly, who actually chairs the committee for the selection of the AF Harvey Prize. He's currently in Singapore, and he wanted also to say thank you very much indeed for your lecture, and congratulations also on your achievements. His question or he observes that Dr. Kuznetsov received the prize previously for his work on dielectric nano antennas. In contrast, you are exploiting the very different characteristics of plasmonic nano antennas. While very different, what this does is prompt him to wonder if there might be scope for using both techniques in combination at some point, and maybe a collaboration between two IET Harvey winners. Mona, what do you think?
Yeah, definitely. We are always looking into new collaboration opportunities. So the reason most of our nano antennas are metallic is that we want to get a plasmonic enhancement of light interacting with semiconductor materials. And most of the metals, mainly gold and silver, show the strongest plasmonic enhancements in the optical regime. That being said, as I mentioned in my talk, we have been seeing a lot of potentials in plasmonic nanocavities, where we couple light coming from plasmonic lights to a cavity that is dielectric material. And there, I think use of dielectrics with lower loss and having capabilities to tailor the electromagnetic spectrum would be very interesting to explore. And yeah, I look forward to exploring these opportunities.
Well, indeed, I think that from an IET perspective, we're blessed by the fact that the prize winners over the years have achieved so much, and indeed are really at the leading edge And indeed, if there were ever an opportunity to collaborate, it truly would be world beating if that were the case. I have a question from Zheyu Wang, who wants to ask a question specifically about gallium nitride and whether that has a place in the sub-terahertz frequency for your work.
That's a very good question. Gallium nitride is definitely a very interesting material with very specific properties that beats more generally used semiconductor devices so far. In fact, I believe already gallium nitride HEMTs have reached cutoff frequencies in the order of 200 gigahertz range or within that regime. So definitely transistors in the lower parts of the terahertz, sub-terahertz range are very promising, and specifically because gallium nitride has very good power handling and electric field handling capability, it is a very good platform for high power operation where some other semiconductors might not handle. That being said, that is more for electronic-based terahertz, sub-terahertz systems. For the type of terahertz systems that we build in my group, which are up to electronic systems, there are challenges. In fact, the power handling, electric field handling capability is very attractive because currently thermal breakdown is a practical limitation in our devices. However, because bandgap energy of gallium nitride is very low, and it's more having photons absorbed in UV or lower visible regime, the lasers that are already developed for terahertz operation are not compatible. These lasers are mainly in the near infrared and infrared regime. These are the lasers I discussed in my talk that provide femtosecond light or heterodyning light. So current technology is not compatible with gallium nitride. One can use nonlinear processes to do optical wavelength conversion, but then considering the efficiency we lose because of nonlinear conversion, it is still a matter of question what kind of gain we can have. That being said, with more advances that we see in laser technology, maybe suitable lasers also emerge that can be used with gallium nitride.
Okay, thank you. Just as a follow-up to that, I mean, are you ever constrained by access to some of the world's leading materials to conduct your research further, or are you always able to get what it is that you want to be able to take it further, forward?
That's also another great question. In fact, a lot of capabilities that our devices gain are thanks to properties of materials. So here at UCLA, we are fortunate that we have a great molecular epitaxial facility for growing different kinds of semiconductor structures. So that has enabled a lot of findings that we had in my group in terms of different nanocavities we developed, or band diagram, band gap engineering that we did for making totally passive terahertz devices. However, there are still capabilities that are not easy to find. For example, there are a lot of opportunities to further engineer the carrier lifetime, resistivity of the substrate by embedding rare earth compounds in the semiconductor lattice. And that's something most semiconductor growers don't like because of the contamination it causes. And our resources are limited when we want to explore those materials. So I keep collaborating with growers, semiconductor growers in different parts of the world to be able to get those materials. But definitely advances on the material front are very much tied to developments we see in the terahertz field.
To try and keep all access open, as it were, through greater levels of collaboration.
Exactly.
Yeah, okay. Thank you. Kiran Rajani asks, and in fact, there are many people who may be asking this question after seeing the lecture, and indeed the level of You explained it beautifully, but if I may say, it was still at a level at times where one actually tried to wonder. And his question, wonder where it leads to. His question was, what are the practical applications of this technology, and how can it impact in years to come the everyday use?
Yeah, very good question. So we should not forget that terahertz field and developments in this field are decades behind what we have witnessed in the electrical radio frequency regime and optical regime. So a lot of great electronic photonic tools that are facilitating our life right now, the discoveries, the basic research happened decades ago. So that being said, of course, we will witness much more applications in years to come. But as we are speaking, the practical applications are mostly in industrial settings for quality control of industrial products. And when I say industry, I'm talking about a very broad scope that ranges from pharmaceutical industry to basically monitor the integrity of capsules and tablets, not only from physical perspective to make sure if the right coating thicknesses and densities are used, but also if the right dose of chemicals are used in the drugs. And these are very important. These are not just cosmetic consistency reasons that we want these features to be always consistent, because these really impact where the drug will be released in the body, and as a result, how effective it will be. On the other hand, in different additive manufacturing technologies and different manufacturing technologies to see the integrity of the products, I gave examples of energy industry, oil and gas industry, aerospace industry. Terahertz is used to really do quality control. In the medical regime, while there is a lot of research going, use of terahertz for burn wound characterization is very robust. Now it is being used on patients, as I gave examples of my collaborators. In general, communication is another regime that a lot of advancement is happening quickly. Basically, terahertz is not the best carrier of communication signal over very long distances because of atmospheric losses. However, when it comes to short-range communication, in areas that there is a massive amount of data to be transferred, this can be a conference center, stadium, shopping center, then terahertz, use of terahertz communication has been explored. Actually, Japan is leading a lot of effort in this area. There are commercial products out there, basically data kiosks where you can download a lot of data, movies. Actually, you can already see it in Japan. They're being used.
Well, thank you. In fact, it leads on to another question, which I think you may have answered already, Mona, but Nathan Brown says that, and in fact, it's worth just saying this, is an amazing and insightful presentation. He enjoyed very much watching the future unfold. But he's very keen to see how the high frequency, and this is indeed what you were talking about just then, and so high data capacity signal could be used to improve communications. Because in the way that you were discussing it or describing it earlier, it's a case of actually putting it in within another bandwidth, isn't it?
Yes, so in general, when we want to transfer data, we generally want to mount that data on a much higher frequency carrier signal to transfer it. And currently we have a very crowded spectrum with all great advancements in communication industry, IoT devices. Our spectrum in the radio frequency millimeter wave range are quickly filling up, and a terahertz band has a lot of potentials. There's a lot of bandwidth available to basically have to use those for high data rate communication systems, but hardware is the real bottleneck there. And as we get better and better transmitters, receivers, the frequencies are also pushed on that front. Now, communication is a particularly delicate application because, I'm sorry, unlike other imaging and sensing technologies, it's not only the performance of a gadget that determines its applicability, but also its commercial viability, its price also makes a big difference. So that is an area that I think will see a big change in the near future. Currently, some of the terahertz devices we build can handle very high data rate communication, but having an external light source, optical components, a complex system makes them not much commercially viable. So as I mentioned, with the help of IET Prize and the financial support it provides, we are looking into integrating all these components on the same chip to hopefully achieve high performance, but also reasonable scalability and cost at the same time to get to that goal.
Thanks very much indeed. And then just raising the prize itself. In fact, before we came on air live, we were talking about the opportunity that indeed the prize brings to allow you to look at potentially less commercially driven pieces of research, but ultimately ones that will take could actually impact to a far greater extent in the future. It would be interesting just to hear a bit about your group itself, how large it is, and how you actually plan that, how you manage the overall group's outputs.
Right. I have currently a group of 10, and I must say I have been very fortunate to work with very brilliant, energetic students from various parts of the world that have their education from different backgrounds, but they very well blended in and basically integrated to build this very interdisciplinary group. Terahertz is an area that there is not much education in terahertz technology at the undergrad level because it's highly interdisciplinary. So the tools one needs to work in this area range from semiconductor device physics to high frequency electronics, photonics, and electromagnetics. That being said, there is a lot of know-how one has to learn to work in this field. It ranges from very sophisticated nanofabrication know-hows to really building instruments that are taken for granted in the other parts of the spectrum. So I was very fortunate that my group, although they were coming from one particular background, they were able to, all of them, learn other know-hows, and they were trained by their peers to be able to come up to speed and productivity pretty quickly to be able to contribute to this technology and the work we do. One thing I want to mention just to those that might not be working in the terahertz field to appreciate some of the practical challenges we have to do research in the terahertz range is that in other parts of the spectrum, you might make a transmitter and receiver, and then you have excellent tools available to characterize their performance. Network analyzer, spectrum analyzer, oscilloscopes, you name it. In terahertz research, we might make a tool, but then maybe the same amount of effort goes to build an instrument to show the performance. And sometimes when you work at the cutting edge research, there is not such a good tool to really show the sensitivity of the other tool. There is a lot of debate in the community about calibration standards. So we are really in deep research state currently till these tools are developed. And I'm fortunate that my students are so quick learners to learn these know-hows, and they're very productive.
It's absolutely fascinating that one's actually got to spend time being able to prove how far one has got, as it were, before one can move on. And that often the test equipment is actually sits behind. But we've got some other great questions. David Hayworth asks, can you use Terahertz device to generate entangled photons?
I haven't done that. That has been done. It is definitely possible. If one uses a nonlinear optical process for generating terahertz photons out of optical photons, the entanglement is maintained. There has been some great work that I have been following that has shown entanglement quality. The approaches that we use in our group are basically, when you want to generate very high power terahertz radiation, you deal with multiple photons. So you might lose that level of entanglement. But for systems that can be cryogenically cooled to be able to work with lower number of photons, that is also possible.
Thank you. Simon Pike has a question. Do you think that plasmonic nano antennas are suitable? Oh, I think we've probably had that, but are suitable for longer range communication applications at frequencies below 1 terahertz? So that's slightly a different question.
Right. They definitely can be used for this application for communication at lower frequencies. In fact, plasmonic nanoantennas work as low as few gigahertz as far as the frequency information is embedded in light, and the bandwidth of the antenna is wide enough, which we make it wide enough to work at terahertz. Obviously, at lower frequencies, it works. But for communication, again, I would like to bring up this question of commercial viability. So if a CMOS-based electronic chip offers very similar or even slightly degraded performance at 100 or 200 gigahertz range for communication, that is a natural choice to be selected for communication because of its low price, scalability, and the possibility of mass manufacturing. And that's what we are still lacking in the terahertz domain with plasmonic devices, and we are hoping with monolithic integration we get to the same point.
Okay, thank you very much. SH asks, I've only got initials. SH asks, what sort of applications? You already mentioned, I think, some of this, Mona, already, but what applications do you expect might be commercialized first? There clearly are already some in the pharmaceutical area that are being used, and as you say, in burns. But where else? Where next, do you think?
One of the domains that we are currently exploring through the startup company that we have is for quality control of the products in energy sector. For example, for quality control of battery electrodes, fuel cell electrodes, these are products that we are relying on more and more as we are trying to be more independent to basically oil and fossil fuels. They become more important. And currently, there is no real systematic way to figure out the integrity of these products during manufacturing. What is done is that after, for example, for lithium-ion batteries that are mostly used in our automotive, electric automotives, and also in our electronics and many gadgets that we use, when lithium-ion battery is manufactured, there is no approach that one can do in quality control along the manufacturing line. Only at the very last stage, when the whole battery cell is formed, some electrical tests are done. Now, these electrical tests are over a very short time. They don't capture a lot of defects. For example, if even the different thicknesses of coatings vary during the manufacturing process, densities vary, they will still allow the electrical performance to be good, but in long term, they will cause fire, explosion, a lot of problems that we hear about it, that lithium-ion batteries have. And unfortunately, there is no way to capture them. And even those products that fail the electrical test, it is at the point that you cannot recycle any material. And but if we have systematic quality control tools along the production line, material can be recycled, and really no electrode can be integrated into a gas cell, into a battery cell, unless its integrity is proved. So this is a huge market. So we have so far seen a lot of interest from battery manufacturers to really solve a major problem in that domain. But in general, that technology is very, very much applicable to any additive manufacturing facility that we see the use of them more and more in industry. One other domain that I see an immediate industrial use is for quality control and basically assurance of electronic products. So currently, the integrity of electronic chips and boards are becoming really a national security issue in US, with different parts of manufacturing being done in different parts of the world. The security, data security, the problem of tampering with electronics is becoming a major problem. So we have been working with Intel to basically, by just looking at terahertz response of electronic packages and circuits, being able to prove their integrity and their originality. From our conversations, I understand that is a very immediate need, that probably terahertz scanners will be used in near future for that application.
I mean, also a lot of counterfeit products as well. So again, I'm guessing that it would be able to double check whether you've got a real product or not, simply because there's no way that at this level of investigation that you can get to at photon level, nobody is going to be able to counterfeit something.
Exactly. And you mentioned counterfeit, you reminded me of another application that we are also very keen. And it's one of those applications that we really discuss it with end users in detail, so we understand the urgency of the need. So in my talk, I mentioned our collaborator with US Department of Agriculture to detect aflatoxins in agricultural food products. This is a major unsolved problem that varies year after year. Like, you don't know, based on the weather condition, insect situation, different kind of pesticides that are used, the level of aflatoxins can vary in products. And there is no non-invasive way to really detect these toxins in food products. Generally, what is done is that regulatory agents grab a small sample set. They do mass spectroscopy to basically detect the level of aflatoxin. And based on a very small subset, they make a decision on a very big lot of products that are going to be transferred to customers or be exported. And obviously, there is a lot of contaminated products that get to the customer. This is a very serious issue because aflatoxin can cause liver damage and can cause liver cancer, actually. That's one of the main reasons behind it, and we really don't have a solution. And we know we have a problem because very frequently exported products that are checked in the destination, they show high levels of aflatoxin, which shows we can easily miss them when we do regulatory inspections in field. So we are working with actually those regulatory agents right now, and we have seen a great potential to detect these aflatoxins in a very non-invasive way and with very high sensitivity, which allows us to really scan every product, and that would be very important for health reasons. And fortunately, with these large area focal plane arrays, we have been able to increase our throughput for scanning, which makes it possible.
Thank you very much indeed. There was just one further question. I've got one to finish off with, if I may. But from Dyson Wilkes wanted to know if the slides were available. Well, the overall presentation will remain online with regard to the IET website. So you've got it, as it were, for Continuum in the future. My final question, Mona, is electrical engineers are really hard to come by in the Western Hemisphere. We're not training enough at the moment. And if I may say, it's really hard to get women into engineering. May I ask, all the way back long before you did your undergraduate degree in electronic engineering, electrical engineering, what was your inspiration? Who was that person who inspired you to want to do work of this nature? And well done them, whoever they were.
I grew up in Iran and did all my education till my undergrad studies in Iran. In Iran, culturally, education is a very important thing. I remember and it's both important for girls and boys. And from early on, you are encouraged to go to STEM field, math and science. As a result, there are also great role models that you can look up to see a success career path in this domain. In fact, these days, the very sad scenery that we see from Ukraine war reminds me of the war we experienced when I was growing up. There was an 8-year war between Iran and Iraq, and we were constantly going to shelter or basically escaping to outskirts of the cities. Schools were closed, and a very obvious memory from those days is that during these times, even schools were closed, like education was continuing. So there were, we didn't have internet at that time, like TV was constantly broadcasting the school courses at homes. Parents, while escaping for their life, they were making sure that kids are really doing their homeworks and they're not falling behind. So culturally, it was a very important part that families made sure it is done well. And even you could see at university, at the undergrad level, the proportion of the number of girls and boys were much more balanced compared to even what we see in West nowadays. So I would say it was something cultural, something that was put in front of me as an obvious path. And there were great role models to look up to.
Well, Mona, I'm so pleased that you had that opportunity. You now truly are an international role model. So thank you very much indeed for answering our questions of IET members. Every success, wish you every success in the future for the grant to you and your group. And indeed, I think all of us are now looking to see, we'll be looking through the newspapers to see advances in technology that's come as a result of your work. So thank you very much indeed. And if I may, thank you very much.
I would like to once again thank IET for this great honor, and I also thank you for this lecture. I hope I have brought more broad knowledge about terahertz to a broader audience, and yeah, look forward to see where technology takes us.
We have all learned more as a result. Thank you. And thanks very much indeed to everybody for tuning in, and thank you for your questions. The lecture will be available to view on demand via IET TV, and it will also be on www.theiet.org/Harvey forever. You can never lose ones and noughts. Thank you very much indeed, Mona, again. Terrific.
Thank you.
Good night.